Hi, we are Morgan and Kunal, and we are going to go over our project for the semester, which was basically we wanted to model a phenomenon that happens in the brain where the brain is basically presented with two or more stimuli and needs to process those two stimuli and decide which of them to respond to and in what order. So first I'll just go over a little bit more about what exactly that means and how this happens in the brain. So the diagram shows the brain and the eye and the visual field. So what we're looking at in this project is the two eyes see a stimulus. It could be food, or it could be a person, or it could be any object, and so the light reflects off that object into the eyes, and then the image is delivered to the brain through the optic nerve, and the brain then has to decide. So for example, if the brain is being presented with two stimuli, it needs to decide which of them to respond to first. So that's what we're going to be doing in our project. So obviously in reality, the brain can do more than one thing at once, but in some cases, for example, when you're choosing between two things, you need to choose between them, and we're going to try and model how that takes place.
So in order to recreate the brain's decision-making processes, we're going to use something called competitive cueing. Competitive cueing is actually relatively straightforward. It's very similar to what we've been doing throughout the semester all along, and it kind of follows some of the guidelines we have listed here on this slide. So if I could just go through this slide. Essentially, it's going to be a cue that's organized by some type of weight. So stimuli that is accepted into the model is going to be assigned a weight, and then it's going to proceed through the model, and those that have a higher weight are going to be able to pass through the model at a faster rate than those that have a lower weight. So those that are weighted less will be given some kind of seizure through the system, so they'll be held and will not be able to pass through the competitive cue as quickly as those that are weighted higher. The neural network itself, which is what we're trying to replicate here or mimic here, is a winner-take-all system. So whatever passes through the model first will win, or in our example, will be the decision. So whatever wins the system will be ultimately what the model, or what we're trying to replicate, the brain, decides upon, whether it's ice cream over peanuts, or red versus blue, left hand versus right hand, anything that you're trying to decide upon. So the goals for this project here are actually pretty straightforward. We're trying to, and they're laid out here in this slide, we're trying to mimic a neural system. We're trying to demonstrate how the weights effectively generate the response of the system. We're trying to see how, or explain how, those weights are linked to external factors. So you're going to see things like proximity, allergies, or prior experience with certain stimuli, how they factor into given weights. And then finally, we want to be able to have the model make a decision and fulfill what it's supposed to do. Essentially make a decision on a given stimuli, what it's going to choose, and then from there have some kind of output. So before we press on into the model that Morgan and I created, wanted to give you a little bit of background of some of the other neural networks that are in use or have been created by researchers. The first one I came across while doing a little bit of background research on this project is the MaxNet model. I don't have a lot of dialogue here on the screen, so I'll just kind of explain it best as I understood it. Essentially, you have a model set up like this, where each node or represents stimuli. Each stimuli is given a weight, and then effectively the weights of those stimuli cancel out, so that they're competing against each other, much like our competitive cueing system, as you'll see later on. These nodes or stimuli are competing against each other, and the node or stimuli that has the highest weight will win because the nodes are effectively canceling each other out. So again, this is kind of a winner-take-all model, and it's similar to what we're trying to present, as you'll see in a little bit, but not the same, as there is no real time element in the MaxNet model. Another common model I was able to come across while doing research on this project is the Hemming net. This is a little bit more complex. There actually isn't a winner-take-all component of this model. But again, each red node represents a stimuli. And this is actually more of the model itself is using stimuli to match with existing stimuli here. It's actually based on these vectors. It's actually pretty complex. It's based on the vector angles here, and there is an associated algorithm with this model that's in our project, and you can look at that at a later point. It's hard to kind of tell from the Hemming net image here, but if we go to the next slide, it'll give you a better idea as to what the Hemming net is really trying to accomplish. So you have these various animal types, and you could see, based on size and domestication, the slope of the line is changing as additional animals are input into the system. And it's using that slope to give you a corresponding output based on the series of inputs. And you see the slope is changing dependent on those inputs. You might kind of wonder, well, okay, this is great. I mean, we can have a slope of different animals here. But how is this really being put into play in the real world? It's actually pretty neat. I'm going to kind of break out of our demonstration here. I'm going to go to a Google website. It's actually something called Google Quick Draw, and it's using this similar, or if not same exact technology, probably a much higher level, to recreate the slope or kind of provide outputs based on inputs that end users give. And I think once you see it, it'll be pretty obvious as to what it's doing. It's actually called Google Quick Draw, and basically what it does is it asks you to draw things, and the software or the program using Google servers will give you an answer as to what you're trying to draw. So if I just hit got it, I can start drawing a cup.
I see square, or bread, or door,
And
or camouflage,
sometimes it's good,
or
sometimes it's
dishwasher.
bad.
I see cell phone. Oh, I know, it's cup.
Figured out it was a cup. So it's kind of using that similar technology. You give it a set of inputs, and if I just go back to our presentation, you give it a set of inputs, and using its prior knowledge, using that slope or that trend, it'll give you an output. So just wanted to incorporate that here and give you an idea as to how some of this work is being used in the real world, and just give you a little bit of background on what our project is trying to mimic or replicate, and some of the work that we've used to create our model and project.
Okay, so deciding on our methodology was probably the most difficult part of the project, because unlike most applications that you might use Arena for, we're not that interested in server utilization or queuing length or the average time that an entity spends in the system. So we asked ourselves, what are we really interested in? And we came up with the order in which entities exit the system, having entered simultaneously. So we decided to use the black box abstraction concept as a starting point to decide how to model this. So we have our input, which is the stimuli arriving at the same time, and we have our output, which is the order in which they exit, so their queuing order. So this comes back to the competitive queuing aspect of our project, where entities entering the system compete with each other to get to the front of the queue first, because obviously the first element is going to be acted on first. So whereas other systems that Canal just went over use a weighted system where entities that have a stronger weight pass through faster, we decided to use kind of a time punishment system where entities that are going to be disadvantaged going through the system are given time punishments, and that delays them getting through the system, so they actually get to the queuing order slower. So this table kind of explains what I mean, where it's basically a translation from the physical phenomenon that we're trying to model and how we're going to represent that in Arena. So when the person's presented with peanuts and ice cream, which is the entities we've decided on, the two entities are created simultaneously and named so that we can then identify them in the report. And then the person is allergic to peanuts, so then the peanut entity is seized for some time, whereas the ice cream entity continues along the system and it's not got this disadvantage that the peanuts then has. And then, so we have a few other ones here that I won't go over because we're going to go over them in the model. Okay, so here we are in Arena, and we're going to go over the actual system and show you how we built it. So, we started out with the creation of our two entities. So we have peanut entity and the ice cream entity. So, like I just mentioned, so basically we have them here. The entity type is peanut, and we want one entity per arrival and one entity in total as well, because we just want to compare between peanut and ice cream. We don't need to have like several of them arriving. And the first creation is at 0, and then we have the exact same for ice cream as well.
From there, both entities move into the group stimuli, which is actually just a batch module. Works as a holding pen for our two entities, so that way they can start through the system at from the same 0 point in time. Then they're separated out with the separated stimuli, which is a separate module, so that way both entities can make their way along the system.
Okay, so then we go on to the sort of filtering out and the competitive queuing segment. So we start with the peanut energy decision module. So what this does is it decides, it asks the question, is the entity passing through this module a peanut? And it's two-way per condition, and if the entity type is peanut, then obviously then it's true. And as we see here, it follow it through, it says true, and then peanut is set back, and this is a process module, which basically disadvantages the peanut going through the race. So it's a delay action. So like we just said, it was going to be a time seizure. The delay type is constant, and we decided to give it a 10 out of 10. So we basically we rated each of the decisions out of 10, and obviously an allergy is pretty severe, so it's going to be 10 out of 10 delay. And that's value added so that we can see it in the report at the end as well. And then we kind of did the same thing with, so the person has a bad experience with ice cream. So maybe it was some kind of like traumatizing experience as a child or something. So then two other conditions again, so it checks if the entity is an ice cream. Okay, if true, so the ice cream's going to go this way. The ice cream gets set back. It's the same kind of thing. We decided that this is going to be a 3 out of 10 severity, and then it's value added again. So this checks if the ice cream is further away, which it is, so the ice cream is set back again. And then finally we added this module just to kind of as a control decision module, I guess. The person really loves chocolate in this case, and so it's going to check if the entity is chocolate, and if yes, then the chocolate's going to be sped up, and it basically gets a value of -1. And then so basically, they finally end up with the dispose module.
Yeah, and the dispose module essentially represents our choice or our action. As we'll see in some of the results in just a moment, ultimately I believe ice cream is chosen, and that's determined based on time through the model here. Okay, so now we're just going to take you through Arena itself, run through the model at least once you can see that it works, and we'll do that now. And of course we'll get an error. Not sure what that is, but okay, we got the model running. You have both entities run through. Take a look at the results. Actually, no, we'll just go to the PowerPoint, which has the results. And here you have ice cream and peanut side by side. The average time in the system is representative of the sum including all the seizures that are implemented in the system. And here you can see that because it takes ice cream less time to get through the system, it is in fact the decision or the winner of our model. So after reviewing the model and running it multiple times, the model is a success. Ultimately, entities or stimuli run through the model, and a decision is made. We saw ice cream was in fact selected, and we are able to determine that from the output that we just saw a moment ago.
So, like all experiments, ours definitely had its limitations. So, the first one was the choice of software. So, I don't think we could say that Arena was really the optimal program to be using for this instance of a model. So, we didn't really use the best features about Arena. For example, its ability to model and keep track of the length of the queue, or the average time spent in the system, or server utilization, things like that. Were not relevant to our model, so we missed out on things like that. And also, it would have been better to have a software that allowed us to use the weighting system rather than a time punishment kind of system. Next, that when we were building the processes, we realized that there was no delay module available to us, and that's something that is, I believe, available in the full version we didn't have access to in the free student version. And that basically, it doesn't mean that our system it still does the same thing, but it would have been, the code behind the images would have been more concise, because it's a module that does one thing rather than a module that you have to set the parameters to for it to do what you want. Our model was really specific to peanuts ice cream, obviously. The only other thing you could probably pass through there was chocolate. So that's a limitation, because you can't apply it to more than one thing. So it's not really useful in that many situations. One thing that might be better is having a predefined list of things that the person is allergic to, or a predefined list of things that the person is like specifically drawn to or really likes, and then check for each of those and run each entity against those tables to see if it corresponds to one of them, rather than like what we had, where you had to have a different decision module for each of those things, where it checks the entity against one definitive food item. So that's just another idea.
So a lot of our future direction on how this project might be taken stems from what Morgan just really laid out in limitations. So the project itself only has the capacity to observe certain specific stimuli that we defined at a prior moment in time. So it doesn't really have the versatility of other neural networks or your own mind. It might be a good idea to incorporate some of the things we saw earlier in the MaxNet or Hemming model, and this might be able to solve that problem of being able to respond to stimuli that have not been previously defined. However, that is kind of stymied by the fact that we used Arena, so another thing would just be to incorporate or use a better software package or programming language where time is not really a decision driver that we see here in the Arena software package.